So the problem with our limit definition is it sure as hell ain't short. So I'd like to be able to try and find some patterns. And from our set of patterns, induce a more general rule. So let's go through the limit definitions for some basic ideas on polynomials. And I'll start with some functions we already know. And let's think about their derivatives. So I have here a constant c. If I use the limit definition to get f prime, I'm going to take our function and I'm going to plug in x plus h. But the thing about a constant is no matter what I plug in, I get the same constant. So when I plug in x plus h, I get c. When I plug in f of x, plug in x, I get c. So the numerator is c minus c. Well, that means that I'm taking the limit of 0. Zero itself is a constant, and when I take the limit of a constant, I get that constant. So this derivative is just 0. Now, this makes sense from an intuitive perspective. What's the graph of a constant? Say again? Unfortunately, all lines are straight. What's special about this straight line? Horizontal. And the slope of the horizontal line is 0. So if this is my horizontal line, then its slope at every point being 0, that makes sense with the visual image in my head. This is also the equation of a line. F of x equals x. What's the slope of that line? The slope of the equation y equals 1x is 1. So if I have a tangent line, it should have a slope of 1. But let's actually go through the construction of our derivative. This function spits out whatever you put into it. So if I put in x plus h, I'm going to get out x plus h. If I put in x, I'm going to get out x. So my limit is now to evaluate this. What happens to my x's? So I'm just left with h over h. But h over h also cancels, and that makes that limit of 1. But that's a constant. The limit of a constant is that constant. And this makes sense. Again, I've got a straight line. Its slope is 1 everywhere. So its derivative, which represents the slope, is 1 everywhere. All right. If I start looking at more and more powers of x, I need to do this multiplication. So I'm going to do x squared. I'm going to do this calculation. That means I need f of x plus h, which is x plus h squared. Multiply that out. What do you get?
X squared, 2x h squared.
So when I go to do my limit, this is the first part. This is the second part. And now I see some lovely things happen. Again, a whole bunch canceling. The x squared at the front cancels the x squared at the back. I have at least one h in everything on the top, so I can factor that h out. And I can cancel it with the h on the bottom. And now, as h goes to 0, this piece is going to go away, and I'm just left with a 2x. Going with our drawing image, the graph of x squared is a parabola. As we go from left to right, this side, the left side, is going down. Those slopes should be negative. The right side's going up. Those slopes should be positive. The graph 2x is a straight line. It's negative on the left. It's positive on the right. This jives with my intuition. I want to keep going. My problem is doing this multiplication. Because if I go to do x cubed, then I'm going to have to do x plus h all cubed. If I want to do x to the fourth, I'm going to need x plus h to the fourth. If I'm going to do x to the fifth, I need x plus h to the fifth. I'm going to be here for a while multiplying all this crap out. Ew. There happens to be a really nice shortcut for multiplying this out. I don't know how many of you have heard of this idea, but it's called the binomial theorem. And it's related to Pascal's triangle. Binomial because there are two things I'm multiplying out, right? It's an x and an h, and I'm raising them to a power. In order to do this, I need you to write down a triangle for me. So what we're going to do is we're going to start with a row that's got a 1 in it. Just a 1. And then to either side of that, on the next row down, I want you to put a 1. See how we went out a little? On the next row down, I want you to go out further and put a 1 out here. And then we're going to do it one more time. The very first row, where I just have a 1, that's row 0. The next one is row 1. The next one is row 2. The next one is row 3. But in order for me to make this triangle mean something, I need to fill in numbers here in the middle. The numbers in the middle come from taking the numbers above and adding them together. So when I go to fill in down here, I get this row. I want you to give me rows 4 and 5. Okay.
1, 4, 6, 4.
And then down here, now the binomial theorem says that what I'm going to do is I'm going to take the numbers from Pascal's triangle, and I'm going to use the row that goes with my power. So notice, way back here we did x plus h squared, right? And x squared, 2xh, and 1h squared. Those are the numbers. So if I want to do x plus h cubed, I need row 3. So I'm going to write down those numbers. And since I'm adding here, I'll be adding each of these. But now I need the x's and the h's. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row 3. So I'm going to write down x plus h cubed. I need row So start all the way on the left and put an x to the highest power you've got. Highest power in this problem is 3, so I'm going to write an x cubed. Since I'm taking stuff to the third power, I have 3 powers with just the x's, right? So I need no powers of h. I'm even going to write it down, h to the 0. As you move over, the power of x goes down every time you move, and the power of h goes up. So here, I'll have an x squared and an h to the first. Here, goes on tight, x to the first, h squared, and here I'll have x to the 0 and h cubed. Now, what's something raised to the 0 power? 1. So I really don't need those. And something raised to the first power is just that thing. So I can write this as x cubed, 3x squared h, 3x h squared, and h cubed. You want to do x plus h to the 4th? You got to use row 4. To the 5th, use row 5. No matter what row you want to expand a binomial, you use the coefficients from Pascal's triangle. Hey, I can do my derivative now, can't I? So if I want to start with f of x being x cubed, I have this. Now I can take my derivative. F of x plus h minus f of x over h. And again, a lot of canceling occurs, a lot of algebra canceling stuff out. My x cubes cancel. And again, I notice that everything that's left on the top has at least one h in it. So I can cancel that with the h on the bottom. And now I'm going to let h go to 0. What happens? This doesn't get changed at all by h. This becomes 0. This becomes 0. The only thing that survives is 3x squared. The advantage to this. Let me go back to Pascal's triangle for a second. Please notice, as I go across here, I start with x to the highest power and no h's. This piece is going to have one h. This is going to have two h's. This is going to have three h's. 1h, 2, 3, 4. 1h, 2, 3, 4, 5. The only thing that ever gets one and only one h is this number. And that's always the row number. This gets the highest power of x, which is the row number. What power of x does this number get? One less. If I were to do this in general, then I would write x to the n, then n x to the n minus 1h, and then stuff with at least h squared. Everything else has at least two h's in it. 3 or 4 or 5, but at least two of them, right? So let's think about doing our derivative. Almost forgot to write my limit in there. F of x plus h minus f of x over h. The first thing that's going to cancel. The xn's themselves. Great. So that means I get nx to the n minus 1h plus stuff with h squared. But that's all divided by h, right? What's going to happen to this h? With the one on the bottom. And all of these things, instead of having at least two h's, now have at least one. But they all have at least one. When h goes to 0, all the stuff inside the parentheses is multiplied by 0. Which means when I take this limit, all of this goes away. And the only thing that survives is nx to the n minus 1. For any power of n. If I am taking the derivative of something with a power in it, x to some power, that's going to work every time. Best part. This matches what we already knew. Go back and look at our previous examples. We had a constant. A constant can be written as x to the 0th power. So if I do the derivative, it'll be 0x to the, wait a minute, what happens when you multiply by 0? We had x to the first, its derivative is 1x to the 0, but x raised to the 0 power is just 1. We had x squared, we got 2x to the first, at x cubed, we got 3x squared. This is making perfect sense to me. This lines up perfectly with the pattern we already created. I should, if I'm really being anal retentive, I should write out a formal logical proof of this and say that this pattern is valid for all values of n and demonstrate why, but really, that's what this is. It's a calculation that goes through and shows you why the only thing that survives is this one lower power. Questions? My favorite thing about this is that it works for any power of x. The only caveat, the only thing I have to be aware of, the only thing I must be absolutely sure is that I am taking the derivative of something of the form x to a power. What I have written is not written that way. But it can be algebraically. How can I rewrite this to make it x to the something? Now I can apply my power law. And I can say that the derivative of this is negative 3x to the, be very careful. The most common mistake people will make here is write negative 3x to the negative 2. The second most common mistake people will make is they'll write 1 over 3x squared. You have to have nothing but a power of x over here to be able to do this at all. Same deal. Because roots are powers, but roots are fractional powers. It still works. I just have to remember to subtract 1 properly. Yes.
On a test, would you want us to revert it back to a fraction once we get it?
That's really your call. I'm perfectly fine leaving it like this, but you are going to see in the textbook that they will not leave negative exponents or fractional exponents. So this would get written negative 3 over x to the fourth. And this would get written as 1 over, well, this goes in the bottom, and x to the 2/3, the third is a cube root of x squared. So I don't care, but the textbook and most online sources are actually going to give it to you in those formats. You're welcome. More questions? But I said I wanted to look at polynomials. Polynomials are made up of pieces that are taken together, right? So I need to think about 2 other pieces in my polynomial building. This is just for powers of x. So what happens when I have a number in front? I'm going to be pedantic for a moment. I don't know what I should do with this extra 3. Let's go back to the definition. I put in x plus h, I put in x, I have 3x plus h squared, I have 3x squared. Wait a minute. That's the same as 3 times x plus h squared minus x squared over h. Chapter 2, section 3, section 4, properties of limits, section 3. The limit law said if I had a constant on the inside of a limit, what could I do with it? Okay. I could move it to the outside, out here. Now, before I go and do anything else, let's consider what's in that box. I am having the weirdest sense of deja vu. I've seen this crap before. What's in the box? Matter of fact, the exact same as our derivative for x squared, isn't it? That's right here. So that is the derivative of x squared. So basically, I kind of took the 3 and stuck it out front and said I can ignore it, just do the x squared. What's the derivative of x squared? So the correct answer here is 6x. If I just have a number multiplied, then I don't have to worry about the number at all. The derivative of constant times thing is constant times the derivative of the thing. If I have any constant at all, I can take it out front. So the derivative of 7 root x is 7 times the derivative of the square root of x. But now I need to know how to do the square root of x. How do I do the square root of x? Chris?
And then be like.
Is that the derivative or is that the original?
Isn't it like 60 equals 60?
In which case it's not negative because this is currently on the top, not on the bottom. Negative powers come from being on the bottom. This is currently on the top. So it would be 7 times the derivative of x to the 1/2. So a 1/2 power is correct, but negative means bottom, and this wasn't on the bottom to start with. Wait a minute, now I can do the derivative. Subtract from the power 1/2 minus 1 is negative 1/2. Everything from here on down is optional. I'm going to do the algebra. So the algebra 7 times 1/2 is 7 over 2. X to the negative 1/2, that's 1 over x to the 1/2. But 1 over x to the 1/2 is a square root. So I get a root, but it's in the bottom this time. See how the difference is with the positive versus the negative, Chris? So really, I was exploiting my rules of limits. So let's go back and look at the rules of limits. Chapter 2, section 3, we had a bunch of rules for limits. I could take the limit with a constant, move the constant outside. I had things about adding and subtracting, right? If I took the limit of 2 things and they were added together, I could take the limit of each one and add them. If I had 2 things and they were subtracted, I could take the limit of each one. The same thing holds true for derivatives. If I take the derivative of 2 things added together, I can take the derivative of each one and add those. I'm writing this in that ddx notation because I like to think of it that way. If I want to do this to a sum, I do it to each piece. But you could also write this in Fermat's notation with the primes. If you like the prime notation better, that's fine. For this application, I prefer the ddx notation. It works exactly the same way for subtracting. If I have a minus sign here, I will have a minus sign here. Rules are exactly the same all the way through. Which means I could now ask you to do the derivative of this. And if I really want to be a pain in the neck, I can say, okay, well, we're going to break it up into pieces. I'm subtracting, so I'm going to do the derivative of the first part, and then the derivative of the second part. Since I'm adding the third, I'll do the derivative of that separately. And now I've got a constant here, so I should pull that out. There's no constant here, so I don't change anything. There's a 3 here, pull that out. And now I'm just doing power rule. Derivative of x to the fourth. There's a 5 in front, 4x to the third. Derivative of x squared. Derivative of x. There we go. I know a large number of people who will go directly from here to here. That's fine. Some people will even do the multiplication in their head. They'll go directly from here to here. That's also fine, as long as you do it correctly. If you had written down here 54, I'd be very confused, and I wouldn't know where it came from. Maybe you meant to write this and forgot the parentheses. So be careful with what you do in your head versus what you write down. By the way, this makes short work of something we did yesterday. What is the derivative of 2x minus x cubed? And that took us what, 10 minutes yesterday? The limit version of this definition is a pain in the neck. This is a lot faster. Unless you are deliberately told to do the limit definition. Don't. Do this. But if you are told to do the limit definition, you should do the limit definition. Questions? A lot of what we want to do with our derivatives involves doing algebra on those derivatives. Typically, when a question is asking where is this going to happen, they're asking for what x values. So I would like to know what x values have horizontal tangent lines for this equation. What's the first thing I should do? Let's make a picture. Grab your calculators, graph this stuff. By the way, I still have those left over from yesterday. I tend to leave those there frequently and just turn them off if I don't want to use them. You go highlight the equal sign, hit enter, it'll change it from highlighted, where it's on, to unhighlighted, where it's off. Then I don't have to get rid of those. I can keep them on hand in case I need them. Your option, it's not a requirement. But I want the graph of this. I see some places where I think I'll have horizontal tangent lines, don't you? I think I see 3 of them. What are the x values? I mean, I could guess, but I don't have to. Because I know that the slope of my tangent line is given by my derivative. And I've told you I want the tangent lines to be horizontal. What's the slope of a horizontal line? The slope is 0. I need to know where my slope is 0. The slope of a tangent line is given by the derivative. So if I want to know where the slope of the tangent line is 0, I need to know where my derivative is 0. Which means I need my derivative. What's my derivative? Derivative of x to the 4th. 6 times 2x is 12x. Great. So I'm going to take that, I'm going to set it equal to 0. Now what? Okay. Because there's a 4 and an x here, there's this, okay, 4x leaves behind an x squared, leaves behind. Now, if I'm multiplying two things and it's equal to 0, one of the things must be 0. So either 4x is 0 or x squared minus 3 is 0. What's the only way to make 4x equal to 0? To multiply 0 by 4, so that means that the x has to be 0. I divided both sides by 4. Here, x squared has to be 3, so I take a square root. Aha! Every number has both a positive and a negative square root. Does this match up with the picture we saw? One on the left, one at 0, one on the right. I can even check. If I hit the trace button, when x is 0, y is 4, and I appear to be up at that top there in the middle, my tangent line should be horizontal there. If I type in the square root of 3, I can type it in just like that. Again, I think I'm there where a tangent line is horizontal. And if I do negative square root of 3, I see the same thing. Looks like I found all the right places. Now, my calculator is stupid. When I type in the square root of 3, it gives me the decimal, because my calculator only knows decimals. And I don't expect you to have memorized the square root of 3 is 1.732. I wouldn't expect you to know that. So we type it in longhand. Questions? Every polynomial we work with can now have its derivative taken. I don't care what the polynomial is. It can be a long polynomial, it can be a short polynomial, it doesn't matter. As long as I have a polynomial expression. This particular polynomial that I just pulled out of my ear is a Maclaurin polynomial. That's why it's called M. But I know how to take the derivative of this. It helps if I rewrite these last couple pieces. Because the over 2 and over 6 and over 24 kind of make me twitchy. So I'm going to rewrite this as 1/2 x squared and 1/6 x cubed and 1/24 x to the 4. And now that looks like number times the power of x, and I'm really happy to see it that way. Take a derivative for me. Now, I will freely admit I did something deliberately weird here. Normally, when we write a polynomial, we put the highest power of x on the left and work our way down as we go to the right. In this case, I put the lowest power on the left, and I worked my way up as I went to the right. It's just a change in the way you write them, increasing order of power rather than decreasing order of power. It really doesn't matter. It's just a convention that certain mathematicians use in certain places. Maclaurin always wrote his polynomials in increasing order for a reason we'll get into in Calc 2. If you are interested in that at all, I can do the explanation, but it's in chapter 9. No, chapter 11, sorry. What's my derivative? The derivative of 1. 0. I don't even need to write it down. The derivative of x, 1. The derivative of 1/2 x squared. We don't have to do them together. We can leave the 1/2. The derivative of x squared is 2x. Leave the 1/6. What's the derivative of x cubed? Leave the 1/24. Now, if you want, you can simplify the numbers because 1/2 times 2 is just 1. 3 over 6. Four over 24. Hey, look at that. Those are really, really close to the same, aren't they? That is actually not a coincidence. That actually is deliberate. I pulled this one out of thin air because of the fact that it does this. Questions? Yes, sir.
That can rid of that square root two, but it's even though it's like that.
Yes, absolutely. Absolutely. Other questions? I can now take the derivative of any polynomial. I can take the derivative of 1 over x to any power. I can even take the derivative of roots of any order with any power in them. Because all I have to do is rewrite them as x to the power. The power rule works for all things that look like this. But that does mean that when I want to look at something that isn't one of those functions, I have to go back to the drawing board. Well, crap. There are lots and lots and lots of other functions. I have functions that aren't just 1 over x, right? We did x plus 1 over x cubed minus 7. We did all sorts of things like that. We did trig functions. We did exponential functions. There are lots of other functions. If I want to do any of those derivatives, I either have to come up with some way to convert them to these, or I need to start over. An exponential function is a function that looks like b raised to the x. The x is not in the bottom, it's in the top now. The x is the exponent, thus exponential function. That number has to be positive, and it can't be 1. What's 1 raised to any power? It's just 1. So that's boring. That's why we don't use 1. All right. If I want the derivative of this thing, it doesn't match any of those other functions up there. I have to do it from scratch. So the derivative of b to the x power is the limit as h goes to 0. F of x plus h minus f of x over h. Ew. That's nasty. But it's actually not as bad as it could be. Because I start thinking to myself, wait a minute, what do I know about exponents? So now I need to dig back in my memory banks to my algebra or my pre-calculus class and go, we did things about exponents and rules for exponents, and I'm adding in the power of an exponent. When do I add powers?
They're the same. Or when yeah. Isn't the whatever is the same?
The power or the base or the whole thing? If the bases are the same. I have this rule that says if I take base to one thing and I multiply by base to another, that's the same as adding the powers. X squared times x cubed, you add the powers, you get x to the 5th. Well, I can use that backwards. Here I'm adding. I'll write it as multiplying. Now, I will freely agree, that's weird. Why would you do something like that? Well, the reason I would do something like that is because now in the top of this expression, I have a b to the x in both pieces. I could factor that out. If I pull out that b to the x, what gets left behind? Say that again. Aha. Here's my sneaky idea here. The limit I am taking. The limit is about h. It doesn't care about x. It doesn't care about b. So as far as this limit is concerned, this number, b to the x power, that's a constant. What can I do with constants that are inside limits? Exactly, Chase. I can put them in the front. Now, at this point, most of you should be saying, this didn't get any better. That's still disgusting, and I don't know what the hell is going on in that set of parentheses. And you'd be right. So I'm going to pull another thing about powers out of my knowledge from algebra class. What power gives me 1? The 0th power. So I'm going to take this 1 right here, and I'm going to write that as b to the 0. Then I'm going to do something else sneaky. And I'm going to take this h that's up here on the top, and I'm going to write it as 0 plus h. So here's the new version. And now I have the weirdest sense of deja vu I've had all day. The thing inside the parentheses looks really, really familiar. Go back to the very start of this problem. What does it look like?
X plus H minus.
Wait a minute. That means that the thing inside the parentheses here is the derivative of b to the x when x is 0. So if I want to figure out what this thing is doing, I need to know what it's doing at one particular spot. I need to know what it's doing at 0. That's really weird. So if I say f of x is b to the x, then the derivative is b to the x times f prime of 0. There's this weird extra number that shows up. Now, that's just weird. grab your calculators for me. I would like you to graph two things. I want you to graph 2 to the x, and I want you to graph 3 to the x. Every graph that is an exponential equation kind of looks the same. They all kind of look like this. If the base is bigger than 1. If the base is smaller than 1, they'll look like this. But since in these cases the base is bigger than 1, they both look like this. Notice that one of them is steeper than the other. The first one, the low one, that's 2 to the x. The high one, that's 3 to the x. I'm going to change my window here because I don't care about the negative numbers. There's 2 to the x. And 3 to the x is a little lower on the left side and a little steeper on the right side. It's just shifted a little. In order for me to figure out the derivative of either of these, I need to know the slope of the tangent line. And I need to know it right here at x equals 0. And on both of these graphs, when x equals 0, I get y equals 1. We said that b to the 0 was 1, so we go through 0, 1 on all of these. Now, I can ask my calculator what's the derivative. And the calculator will do a table, and it'll zoom in and it'll tell me the derivative. Second, calculate. Option number 6 says do a derivative. I can say, I want you to do a derivative. And when I hit enter, it'll say, what equation do you want to use? I want to use 2 to the x. I want to do it at 0. I hit enter. And it shows me that dy dx is 0.6931472. 0.7-ish, right? Let's do this again. Second, calculate derivative. But this time, instead of doing the 2 to the x graph, I'll hit the down arrow, and I'll do it on the 3 to the x graph. What do you get when you do it on the 3 to the x graph?
1.0986.
Perfect. Those are weird numbers. It would be better if I could find the number where this result was 1. It turns out that I can. If we let b equal the number e. In other words, we're using e to the x. Then f prime of 0 is equal to 1. As a matter of fact, this is a good way to define where the number e comes from. It's the curve we picked that looks like these that has exactly a slope of 1 when x equals 0. Not 1.09, not 0.7, but exactly 1. Well, wait a minute. If I do that, then the derivative of e to the x is e to the x times 1. Derivative of e to the x is e to the x. Holy moly, wait a minute. The derivative of this function is itself. The derivative of x squared was 2x. The derivative of x cubed was 3x squared. The derivative of x was 1. The derivative of the square root of x was 1 over 2 square root of x. It's something different. Not this time. This is an exceptionally unusual function. As a matter of fact, it is the only function whose derivative is itself. Now, that f prime of 0 number was like 1.098 for 3 to the x. It was 0.693147 for 2 to the x. Those numbers have to come from somewhere. When we use e itself, e is between 2 and 3. If you grab your calculator and you type the other e button, okay, when you go to type e to the x, you usually use this button right here where it says e to the x above the button, right? But there's another e on the calculator, all the way over here above the dividing sign. You'll notice it doesn't have an x on it. It's just e, right? That's actually the number e. It's between 2 and 3, because 2 to the x gave me 0.7, and 3 to the x gave me 1.1, and I want 1, it should be somewhere in the middle. This is sometimes called the natural base. It's also known by the person who wrote up one of the first pieces that did it. The first person to work in base E extensively was the guy by the name of John Napier. And so it's sometimes called the Naperian base. John Napier, by the way, was a mathematician in England in the 1600s, 1700s, somewhere back then. And he was working on a method for doing very large calculations, which involved exponential equations. And he found a nice, easy way to do logarithms, because a logarithm just takes powers out of bases, right? Well, that's why ln, the natural logarithm, uses the natural base. It's also called the Naperian logarithm. He developed a set of tools, physical rods, that if you lined up the number you wanted the logarithm of on the top, you could read off the logarithm on the rods. Now, unfortunately, because it was England in the 1600s and 1700s, there was this weird thing in England called debtor's prison. If you owed somebody a lot of money, they would throw you in jail and make you work it off. The rumor was that Napier, while being in his cell, made his first set of tools out of his cellmate who died. They're called Napier's bones. I have no idea how true that is or not. We have yet to find a set of Napier's bones made out of bone, but we found them made out of ivory. The history is just bizarre, sticks with you in weird ways. Napier was working off his debt by doing calculations for people. So that was how he was paying his debt in debtor's prison. This is the only function I know whose derivative is itself. That makes it really special. It also means it can be part of other things, and trying to find other functions that have nice relationships to their derivatives is also an interesting challenge. Okay. This is the end of chapter 3, section 1. We did all of chapter 2. We did this piece of chapter 3. Our exam next week covers all of that. All of chapter 2 and chapter 3, section 1. Tomorrow, You should come with questions on the homework for 2.7, 2.8, and 3.1, and the exam review. Whatever questions you have, I will answer tomorrow. On Monday, you turn in that homework, I do something else, and on Wednesday, we take that exam. I will see you all tomorrow. Have a wonderful rest of your day.